So what we have here, up the top we have basalt. It's 5 to 50% porosity. So the 5% will be the unfractured, pretty much probably vesicles only. The 50% will be the highly fractured. And as you can see, we've got gravels, 24 to 44. Then you got coarse grains, so they're pretty much in between the 30s and 40s and 50s. And then you got clay, you got 40 to 70. And then we got effective porosity, so that's what it can travel through. And as you can see, clay is pretty small, 1 to 18. And basalt is pretty much just the fractured rock. And then you got the hydraulic conductivity. So this is the 1 meter, how long it takes. Okay, for 1 second, how far it travels in the actual rock. And as you can see, basalt it can go up to 2 centimeters per second, or 0.2 meters per second, 0.02 to very small. And as you can see, all the other rocks travel, silt types travel at different times and different speeds. So clay is the smallest, so it travels the least for every second. And basalt can be the largest, but gravels are what you really need. So water travels very far in gravel, so 2 centimeters per second, roughly about 1.5 kilometers per day. That's how far water can travel in basalt as well as gravels. So what you're looking at here, so we've got the gravel. So in that aquifer right there, the basalt would travel the furthest per day. But if you've got a large block there, it's not going to go through it. The crack, that distance you can travel through there is probably similar to gravels. So probably about 1.5 kilometers per day, because it doesn't look like there's any weathering or clays or gravels or silts clogging up those fractures. So they're pretty clean, so it should be easy for water to travel through it. But when you get down into this lower section, you can see this is really fractured. It's really weathered as well. So this would contain a lot of silt sized particles and clay type particles, which would reduce the travel distance of the actual basalt aquifer. So up the top where that plant is, right there, should be a fast pace because it just looks gravelly with not that much silt at the moment. But just underneath, it's fairly weathered, so this might have been an erosional surface at one time, and it contains a lot of silts and clay, so the conductivity of the water is a lot lower there. So the water is going to dissipate a lot more in the upper surfaces where it has an easier flow through. And if we look at the rest of the basalt, you can see that it's all fractures are here. The conductivity of the water will probably be quite fast because there's a lot of fractures without any infillings of silts. So it has had time to weather. And up here seems pretty clear, pretty clean. And here's an erosional surface, so that's pretty much just clay there. So the conductivity of the water, so it would also retain water a lot longer. So the water would disappear here quite quickly. Here it would retain it for a lot longer, so if you're looking for water, that's where you need to look for it. So that's the conductivity of basalt. It does change with the type of material, which is a bit different than siltstone and sandstone, which generally doesn't, it's already eroded and weathered material, so generally it's a smaller size that particle is going to get. But this basalt's made out of crystals, and at the surface it is an unstable matrix. So this is mafic basalt, so it has silica deficient, and a lot of the crystals in it are what it's made out of: hornblendes, amphiboles, feldspars, something like that, are not really stable at the surface. So they do weather to this type of clay here. So this is black clay, so it has a lot of organics. What you need is a whiter clay. So that clay around there is a brownish colour, so it has a lot less organics in it. It's more in its natural state. Also, that retains water pretty well. This one dries very quickly. So anyway, that's montmorillonite clay. So that's basically just an introduction of a basalt aquifer.